Hello, my name is Rasmus Krislund, and I'm an external lecturer in the connectivity section at Aalborg University in Denmark. In this video overview, we'll look into wireless fundamentals, and I'll be talking from a context of smart metering in order to be able to provide you with some practical examples. We will only be looking at two topics today, the link budget and the coverage that this link budget translates into. We start by looking at path laws. Here we have an overview image of Aalborg and a simple illustration of a base station in one corner and an example installation of a smart meter in the other corner. Often the line of sight path is blocked by, for example, a tall building or similar. So instead the signal will take another path. The wireless signal is emitted in all directions, and once it hits a hard surface like a wall or a rooftop, it's reflected. And then after multiple reflections, it will finally reach the base station. And there will be multiple of these different paths being reflected on different surfaces and so on. So the signal components reaching the base station will be combined, and this is basically what's causing the phenomenon of multipath effects. This gives a great variation of the signal strength, and I'll continue and talk about that at a later point. Penetration loss is referring to the attenuation when going from an indoor propagation environment, for example, to an outdoor propagation environment. So penetrating whatever installation we have for our device. For smart metering, we are usually talking about three archetypes of installations. We have one at ground level, maybe in the scullery, where the water pipes or the pipes for district heating is entering the building. It can also be in the basement. This is referred to as indoor. And the attenuation going from the scullery and outside, or from the basement and outside, is different. You can probably hear it from the naming. Light indoor is providing one penetration loss. Indoor is a bit higher penetration loss, and then of course deep indoor, where we have the meter installed in a pit in the front yard. And due to the construction of the pit, at least in European standard, it's a concrete pipe where the meter is installed inside the pipe, but approximately 1 meter below ground to avoid frost. And this is attenuating the signal quite significantly, especially if the pit is sealed with a cast iron lid. And what we experience when we have these meter installations corresponds more or less to the penetration model that is provided by the 3GPP, where light indoor, indoor, and deep indoor respectively have an average penetration loss of -10, -20, and -30 dB. This means that within the first few meters of the signal propagation, it's already heavily attenuated. For example, for indoor, having penetrated the building, coming out to outdoor propagation environment, we only have 1% of the original signal strength left to do the rest of the propagation up to the base station. If we look at the link budget, or define the link budget, we have the transmission power at some level, depending on whatever device is transmitting. Then we have the antenna gain. And ideally, the antenna gain would be positive. So amplifying the signal, at least towards a certain direction. But when it comes to small IoT devices, where the area that's reserved for the antenna can be very, very small, it's not uncommon that we actually have a negative antenna gain. So actually it's a loss. So we lose a bit of power emitting the signal into to the air. Then we have the penetration loss, as I mentioned before. This is at least in some cases, a fairly heavy penetration loss, a fairly heavy loss that we have in the very beginning of the propagation of the signal. Then we have the path loss. So this is the loss going from the outdoor propagation environment up to the very base station. There are different models to model this path loss, but we'll not dive into that in particular in this video. Then we have reached the base station, and here we usually have some very high gain antennas to lift up the signal after it has been attenuated quite a lot. In a smart metering context, we are calling the base stations data collectors, because that's basically all they do, collect data. The received power in the base station is having some level, but depending on the technology that we're using, we may be able to extract an additional processing gain by processing the information in the packet. Not the payload, but all the redundant information that the technology is transmitting along with the payload. And this is then the level of the received signal that we can decode in the receiver. Now, if you assume that this received signal is the lowest signal possible, so at the lowest level where the receiver is able to decode the signal successfully, then this refers to the link budget. So if we put this on a definition, then the link budget is defined as the total attenuation a signal can endure between the transmitting antenna and the receiving antenna and still be received correctly. And if we put it on an equation, we write it like this. So we have all the losses, the penetration loss, the propagation loss, all the gains that we have in the link, the antenna gain, which may not be a lot, especially not for small IoT devices, and and the sensitivity of the base station. That may vary with the hardware implementation, of course. When we are planning coverage, we need to place base stations in an area to establish coverage for the devices that are distributed in this area. If we consider this 3DPP model where we have the -10, -20, -30 dB penetration loss representing different installation types, then the resulting coverage or the experience coverage, depending on where your device is installed, will be very, very different. This is illustrated with these circles here. If we have a light indoor installation, then the part of the link budget that is going to be used for penetrating the building will not be that much. So there's a lot of the link budget that could be used for propagation, for path loss. That gives us a large range. This is why we see that the green circle is by far the largest. If we have deeper indoor installation, then we have a large penetration loss. So the amount of the link budget that is left for propagation is less, meaning that we have to be located closer to a base station for our received power to be above the sensitivity of the base station. And if we were to establish coverage in this area, we need to install more base stations, as I said. If we are planning for light indoor installations, then we can place a base station here. You can see that the two green circles are slightly overlapping, and we could place more base stations with a similar distance and get a similar overlap, as you can see. And then we would have at least an expected coverage for light indoor installations. If we were to plan for indoor installations, the yellow circles, and we had to create a similar overlap between two base stations, they need to be located closer to each other. And as you can imagine, if we plan for a deep indoor, they should be located even closer in order to have coverage where the deep indoor devices will never be further away from a base station that the signal that is being received from them will be above the sensitivity of the base station. And remember, the sensitivity was the least or the lowest signal strength where the signal could be decoded successfully. So depending on what installation type you're planning for, you would have very different density in your infrastructure. If you're planning for deep indoor, you'll need to use much more base stations to cover the same area, whereas if it were light indoor, you could do with only just a few base stations. If you had a coverage designed for light indoor installations and you had a deep indoor application, then you would experience a lack of coverage in the edge of all these green circles. So devices located in deep indoor installations would experience insufficient coverage. They would not be able to communicate with the base station. If we look at the signal strength, it will, due to this multipath effect that I mentioned briefly in one of the first slides, cause a probability distribution for the signal strength received by the base station. The mean value will represent the signal strength coming from the main path, but due to these multiple signal components from other paths, it will vary around this mean value following some distribution. In this case, I've just used a simple normal distribution for convenience, and the standard deviation of this normal distribution would be given by would be a result of the penetration and the variation that we see from the penetration loss, and the shadowing, meaning obstacles in the signal path causing the signal to propagate through other paths with multiple reflections and so on. If we have a sensitivity or an RSSI threshold lying here, then the main part of these RSSI samples coming from this device would be above the RSSI threshold, the sensitivity, meaning that we would be able to decode the signal correctly. But there would be a non-zero probability that the signal strength would be below the RSSI threshold. This is what we call the outage probability. Of course, we would prefer if this outage probability were low, and we can actually design our infrastructure for a given outage probability. If we design our infrastructure after that, the mean value or the main path from all our installations would give a signal strength at the base station that would be a certain distance from or above the sensitivity of the base station, we refer to this as the design margin or the fade-in margin. Then we could ensure that only a certain outage probability would cause signals not to be received. Or in other words, we would introduce this design margin to absorb some of the variations that we see in the received signal strength. So we are basically allocating some of the link budget for absorbing this variation. So this part of the link budget we would not be able to use for additional range. We would actually effectively reduce the range to be able to absorb some of these variations in the signal strength. If we take the same normal distribution as before and plot it as a CDF, here I've put in an x-axis relative to the mean value, because that would be convenient in a minute. If we design for an outage probability of 20%, you can see this line, horizontal line, at 20%, and it intersects our CDF with a distance to the mean value of approximately 9 dB. This means that to achieve an outage probability of 10%, we should ensure that the mean value from our installations would never be below 9% above our sensitivity. So we're effectively taking out 9 dB from our link budget and allocating them for the variation that we see in our received signal strength. So in 20% of the cases, we can assume that or expect our packets will not be received due to the RSSI being too low. If this is too much, we can design for a 10% outage probability. And as you can see, we would then need a larger design margin. We need more of the link budget to absorb this variation. And if 10% is still too much, well, then we can take out even more of the link budget to allocate for the variation. 17% of the link budget is a lot, and that might not be feasible due to the reduced range. As we saw before, if we were to account for a penetration loss of 30 dB, we would need much more base stations. If we then also should account for a maximum of 5% of the transmission being below the sensitivity, then we would need to take out the 17 dB additionally from the link budget, creating an even denser infrastructure. And that might not be feasible. So we probably would need to be able to cope with some outage probability. Here I've just illustrated the path loss, the coupling loss of two different frequencies using a very simple propagation model. This is the freeze model, and due to the different frequencies, we get two different traces of the coupling loss. If our base station had a sensitivity of, for example, or a maximum coupling loss of 145 dB, it translates to a link budget of 145 dB as well. You can see we would have an effective a communication distance of 4 kilometers for the 868 MHz band and roughly 8 kilometers for the 434 MHz band. By the way, these are two frequency bands commonly used for IoT applications. So it's not just completely random frequencies. If we were to introduce a design margin of the 9 dB, then we would effectively reduce our range to half. So as you can see, we would need much more base stations to cover the same area if we just introduce the design margin of 9 dB. So this is the exact same effect as accounting for a certain penetration loss. So to wrap up, in this small video, we have defined the link budget, looked at its different components, and we have seen what that translates to into to coverage in terms of design margins, how design margins are used to absorb the randomness of the wireless channel. As a result, this will affect the density of the infrastructure that we are planning. This wraps up the video on a few selected topics within wireless communication. Thank you for your attention. Stay tuned for more videos from the connectivity section. Bye.